Okay. Yeah. So, thanks also to the organizers to invite me to the final workshop on the final day to give some ideas about future trends in lattice QCD simulations. Okay, maybe first of all, just maybe some sources. So I gave a review last year at the Lattice conference, and you can find the proceeding on this link. There were some reviews at the Lattice this year from Peter Boyle about a similar topic, basically, advances in algorithms for solvers and gauge generations, and also a nice review talk by Gauthier Canva about flow-based sampling for lattice QCD. And okay, here I don't have a lot of time, so I just will show some small selection of methods which might be used in the future. And maybe also additional to the ETMC work I'm doing in Wuppertal, we're working on methods to simulate NF equal 3+1 fermions, and this is based on the CLS setup, so maybe just to not be confused during the talk. Okay, so the content of the talk will be, okay, so just about the simulations, but there's a framework. So first of all, I need to motivate. I mean, if one looks in the future, there might be drivers for future simulations, and this is coming from the physics, so just we'll try to shortly motivate it by talking just about G-2, and then I also need to discuss what is the hardware doing, so what are the hardware trends to understand what kind of algorithms can be run on these new supercomputers, and then at the end I will just go over these three things, larger, finer, and higher precision, and discuss some algorithm idea on this. So G-2, we had a nice review talk by Tom Bloom this on Tuesday, just maybe a short motivation for the simulation. So we had last month, there were the new results from the muon G-2 experiment at Fermilab, and they're tiered down their previous error by a factor 2. By making some improvements to the detector and also measurements, you can take a look to this talk here on YouTube where they explain this. What this means for lattice, so this is basically a summary of, so a lot of lattice collaborations are measuring G-2, and the best, the highest precision results in the moment which we have is coming from BMW, and this is still the old experimental error. And so what does this mean for the lattice is basically we should we should try to match this precision, which means we have to tear down our errors by at least a factor 2. If we can look at this, from what are the errors are coming. So I think from the BMW paper, they make a breakdown of the error sources, and I think there are also a lot of different other physics motivations for doing these 3 points. So basically, first of all, we need larger lattices of up to. There were a workshop last week from the G-2 theory initiative, and I think one thing was to go to control the finite volume effects, which means to have lattices of the size of around 11 femtometer. So this is one thing. Then going to the final lattice spacings also tears down the error. If you can see, basically here's a continuum extrapolation, and if you simulate here, and if you have the same precision here, you just minimize the continuum error quite a lot. And surely one needs to improve their methods to get higher precisions. Okay, so this is done on supercomputers, on machines. So let me just give you short overview over the trends in the moment. So this is actually taken from Peter Boyle table of his plenary talk. So what you see here is basically the development of the sustained floating point performance over the last 20 years of some top machines. So in blue, you see the blue gene machines, and now we have this red point here is coming from Frontier at Oak Ridge, the first exascale computer in the US. So which means there's a lot of computing time available. What is not so nice is the development with the bandwidth here on the node. So there's a ratio of floating point over the memory bandwidth, and you see this goes up. So it was in the blue G machine 1-to-1, and now it's here on frontier at 15. And the same with the interconnect, which is even worse. This means their bandwidth capacity does not grow as fast as the computation, and this means basically new paradigm for HPC in our fields. It's better to parallelize embarrassingly, so just start a lot of different jobs as to really strong scale on the whole machine. So the blue gene days where you could scale the solver on the whole machine are over. So this means for algorithms you would prefer, in principle, computational kernels with higher algorithmic intensity, so which does not depend so much on memory bandwidth, and also algorithms on communication avoiding would be preferable. Okay, so let me come to the 3 different points, to the algorithms. So algorithms for larger lattice sizes. So usually what we are using for simulations is a hybrid Monte Carlo. So this means we are doing molecular dynamics. And this basically requires, so the question would be how to scale this up to larger lattices. So the molecular dynamics requires that we start from a configuration and update the physical degrees of freedom continuously. And so we have basically to scale this up. One thing is we have, if you go to larger lattices, the computational cost increases. On the other side, this we can fight only by doing strong scaling. So if the strong scaling window does not scale as well as the computational cost, then this means that the simulation time increases. And this we saw basically on here of a picture from 2020, going from 64 cube to 96 cube, our time per MDU increases basically by this curve. So clearly to go to larger lattices is then quite difficult. So what means this, what one can do to overcome this, one can try, so I will take a look to the solvers, maybe some words about the integrators, and then maybe some ideas to exploit parallelism. Okay, so one algorithm which is also communicating avoiding is based on domain decomposition. So the idea of domain decomposition maybe is known, but so what you do is you decompose the lattice into blocks, and then basically you can define theoretically a block operator which operator on this block with Dirichlet boundary conditions, which does not communicate, which does not need information from the neighbor blocks. So this means, for example, for the determinant, the determinant can be split up into a global complement, a Schur complement, and then local determinants of these block operators. And this can be also used in solvers. For example, in the case of the Schwarz alternating procedure, you can precondition your iterate in the Kirchhoff subspace by applying the inverse of the block operators, which then does not need any communication between. So if you assign at least 2 blocks per node, you don't need to communicate between nodes. And this kind of preconditioning works well for the small eigenvalues of the Dirac operator. It's shown here. Basically, it can dump the error of belonging to the large eigenvalues. And in combination, okay, so then truly to have a good preconditioner, you need to act also on the small eigenvalues, and this can be done via capturing the low modes, and this can be done by defining a coarse grid operator, where with suitable projection operators, which are basically created on approximation of small eigenvalues using this local covariance condition. And so in combination with the smoother, so with this SIP algorithm, which act on the small eigenvalues, on the large eigenvalues, and coarse grid projection, which act on the small eigenvalues, one can get multi-grid preconditioning method, and we have now, for the Wilson case and the twisted mask case, powerful solvers which speed up the solution by around 2 magnitudes. In the case of staggered and domain Wall fermions, it's still under development. There exists some solutions it's working, but it's still under development. Okay, so then this is a break-up. So if you combine the smoother with cross-grid operator, you can act quite well on all the eigenvalues of the operator. So what does it mean for applications on supercomputer? Basically, this is a breakdown, what the different pieces are, how they are scaling. So the fine grid operator scales quite well on GPUs, while the coarse grid operator, the scaling breaks quite fast down. To overcome this, so if you want to use multi-grid solvers in HMC simulations, we are limited by the scalability. So as I already showed, in strong scaling due to the small grid size of the coarsest operator, but we are also limited from below by the memory, which is coming from the projection operators. And okay, one gets additional overheads due to the setup updates, which one needs for updating the projection during the HMC. Okay, so there were some improvements to improve the strong scalability of the multi-grid, and here is just some overview over this. So basically, the development here in twisted mass, looking some years ago, we had by adding GCR deflation restart algorithm, one could break down the solving time towards 8 seconds, and also development on the CUDA side coming from by implementing single precision by implementing single or half, so by starting from mixed precision, by implementing mixed precision procedure, going to half precision and using communication avoiding algorithms on the coarse grid, one could break down, speed up the time to solution to 1 second. So in Wuppertal, we're currently working on porting the DDR-FMG library to C++. This will be suitable for testing these new algorithms to speed up the coarse grid calculation. There will be also added GPU accelerator. There will be added a GPU accelerator smoother, and we are currently trying to. We have also open boundary conditions, and we are working on a comparison of different multi-grid methods to see how they performs. Okay, so how is the status of the integrators? So usually we are using nowadays basically a good collection of higher order integrators are given by this Omar Young, Muir-Glott, and Falk paper. For example, one can use this force gradient integrator, which is based on the secondary norm scheme, where you have basically this force gradient operator coming here as a C. There is a trick. There's a trick. So this comes with a second order derivative. There's a trick by Lin to approximate this second order derivative with 2 first order derivatives. So it's simply to implement. We implement this in OpenQCD, and we are also currently tuning this, and I think there will be results soon on this. So to break down a bit the developments in case of the HMC. We started 10 years ago with a fully fledged CPU package which were running on the Blue G machines, and we had basically this node hour per MVU. And as we added the multi-grid solver to accelerate the HMC simulations, we could break down this cost by a factor 100. And now by enabling force calculations on the GPU, this factor is further breakdown to by a factor 10. And this makes basically simulation, if you think about it, so if you extrapolate this to 192 nodes, this would make simulations of this lattice size with 100 node hours per MDU more or less possible. Yeah, sorry. So the question is there, I mean, this is now just done in the usual way that we ported the solving onto the GPUs. The question would be, are there additional ways to accelerate HMC simulations? And I think we also had a discussion on Tuesday where I just also pointed this bit out. So one thing to overcome maybe, or one idea to overcome this communication bandwidth problems between nodes is to go back to the DDHMC. So this the DDHMC, the idea is to do preconditioning via domain decomposition. So you split up the determinant into a global show complement and to the product over the block determinants. And then you can integrate the local parts on a finer integration scheme like the global parts by freezing the boundary conditions between the block operators. And if so the difference to 10 years ago is that on novel HPC nodes you can increase the domains quite to a larger size, which means this will utilize the on-node performance, and you can avoid communication by doing most of the works on the local blocks. And this is basically in the moment investigated by Peter Boyle and collaborators. So another way to utilize the computational power of these large HPC machines would be to parallelize this via rational HMC. So just to line out the idea, you just rewrite the determinant into the nth root over n products of the nth root, and then each of these pieces can be distributed to different local partitions, and you can basically then run each of these local partitions on these different partitions, and you need to exchange then the forces, communicate that in the forces only. Just to comment on this, basically rational approximation can be combined with multigate. We're doing this in our 1+1 simulation on the CPU, where we combined the multi-mass shift GG with DDR-FMG. Okay, so let me come to another challenge, going to final lattice spacings. So as we know, if you go there, we have topological freezing, and this is likely scaling with a to the power -5. So which means simulations below 0.04 femtometer are out of reach with periodic boundary conditions. Okay, one could use open boundary conditions. But if you want to stay with periodic boundary conditions or because of other things, one needs to fight this large scaling. So the question would be is how we can fix this topological freezing. And a way to do this, we can take a look to the concept of the Markov chain Monte Carlo. There we can break down this basically in two steps. Usually we have some proposal where we propose a new gauge configuration, and then we have an accept-reject step to accept the proposal. And algorithms which would be topological, which would unfreeze the topological charge, would be if the proposal can decorrelate this or has a high topological tunneling rate, and on the same side one has to verify that the accept-reject step has a high acceptance rate, and this is usually quite difficult if one do just some proposal, because the acceptance rate naively drops as e to the power -v with a volume, basically. So let me give you some ideas on the work of the field, to come up with ideas to fight this topological freezing. One idea just recently published by a group in Wuppertal, by Timo Eichhorn and Christian Hörbling and collaborators, is based on metapotentials. So basically, what you do is you want to enhance the tunneling rate between topological sectors. So you add basically a potential to your action, which allows that the topological charge is tunneling. However, so this is working quite well, as you see, without metapotential, and with metapotential, the topological charge is walking around. The problem is you don't want to have this term, so you need to get rid of this afterwards, and you can do this by reweighting. But another possibilities which they proposed in their recent paper is to use multi-tempering. So you have a chain without the potential and a chain with the potential, and then at some point you swap these two chains with this swapping probability. And the nice thing, if the action is the same like here and here, and only the difference is a metapotential in this accept reject step, in the swapping accept reject step, only the metapotential are included. And actually, they got a relative high acceptance swapping rate for this for a lattice of 22 cube. You surely get some overhead due to the metapotential, and you see the decoupling, the length is quite sizable. They still have to understand how this scales with the volume, and if this scales well, I think adding fermions might be straightforward. So this multi-tempering, there are earlier works on this, and one of this work, I think Claudia is also here, is published basically in these papers. The idea here is a bit different. The idea is also based on multi-tempering, but the idea is to include a defect on the lowest level, so a defect like a cube, which is like an open boundary cube. And the idea is that with this cube, which acts like an open boundary, the topological charge can flow in and flow out. And then on the highest level, you get rid of this defect. So you have, and then the swapping rate is just given by the difference of the actions between the different levels, where you have only this defect, so only gauge links. Yeah. They showed that for SO6 this works quite well, so it's here showing off the history. I think in this multi-tempering thing is that the autocorrelation function could become quite non-trivial if you don't see some if you might not capture some of the correlations which are there. This is usual definition of the autocorrelation function. So going even further, one can combine the multi-tempering approach with this sterilizing flow approach. This was shown by Dan Heckert at the Lattice this year, a work by the MIT group. So the idea here is to basically what you're doing is you use a sterilizing flow to map between different levels. And what happens is basically you get Jacobians into your accept-reject step term, and you flow from one level to another level. So basically, you get some modification of the gauge configurations which you flow then. And so this is tenable. And doing this, they get with three levels. Okay, here is multi-tempering between three different beta values, and they show that they get quite high they can get a good acceptance rate between these different betas, and you see that you get a quite nice fluctuations of the topological charge at this beta value. So let me give you some short overview over the flow approach. I think Julian yesterday gave a nice review on this, but let me also give you some just how this works. So the idea is you start at a uniform distribution, and then you try to create a map into your target space, and you can do this by adding coupling layers between to approximate this map. And then you basically get a training condition. So you feed these coupling layers with neural networks, and then you can train then these neural networks by minimizing the distance between your distribution your distribution of your flow compared to the distribution of your target distribution, which you want to have at the end. And the nice thing is that basically you know this distribution, so you can use this then to generate configurations by using just Metropolis exception check steps. So by generating a uniform distribution, flow them to your target space and exception check them with your target distribution. And due to that, then the configurations are independent from each other if the acceptance rate is quite high, and they show this that basically you see that the topological charge is fluctuating very, very nicely due to this decorrelation. However, if you go to larger volumes, you still have you get back the bad volume behavior, and then the acceptance rate breaks quite fast down. So to overcome this, what you can do is basically you can try to localize the flow to domains. So you can do this by basically fixing the boundary links and only have active links within the domain. So basically only flowing and only updating the links within the domain. And yeah, this is possible here in 2D U1. And you get for lattices of size H, acceptance rates which are sizable. And then it's trivial to generate large lattices because you can just update, you can just divide the lattices in small domains and update each of this domain, and you get this configuration of larger sizes. To go into, I worked a bit around with that, and then the thing was that what you do is basically in this approach is you start from a lattice size. You don't touch the lattice size, but you flow from a uniform distribution, so a quite coarse lattice spacing to your target space, which has a fine lattice spacing. So this is kind of the physical box size is. You project them from a large box size to a small box sizes, and this might be not the best way to do. The idea is just to try to start from a small box and project into a big box, but this is quite rather difficult. So the idea was to do this with this flow more effectively. So what I tried out was to just start from one plaquette, uniform, randomize this, and then use the flows to distribute the fluctuation into the lattice. And by doing this, we want to have topological transitioning. So one has to modify the training condition in order to get topological tunneling doing this. Otherwise, if you don't modify the training conditions, you would just enter in the same topological sector. But one can train this, and one can tunnel by just only changing one plaquette in the topological sector. So this is still in pure gauge. So the question would be how to combine this with fermions. And the idea here is, again, using domain decomposition. So you can basically split up their determinant into a global piece and into block determinants. And then the idea of this algorithm is, first of all, propose new gauge configuration with the local flow, and then accept and reject the local determinants, and iterate this until one has a sufficient updated local lattice, and then one do accept reject with a global weight. And doing this, one can get rather high acceptance rate as shown here, basically, so above 90%. And that this approach also enables topological tunneling, as shown down here. So we have these fine-graining flow GCs, which is where I only updated one of the plaquette and smeared this out. This is combined with an HMC step that also more links are changed. And then this flow GC is just updating each blocks, and then after one global update, one shift the lattice and update other logs. And compared to the HMC, you see that the HMC, the tunneling rate, is breaking down for large betas, while the other states are rather constant. So the next step would be here to go to test this for D, and the question maybe is one can combine this with multi-tempering. Okay, so this is about the going to finer grids. Let's go to the high statistics. There we heard that there are some problems. I think also Gupta in his review talk, he pointed this out. So one thing is that we have this signal-to-noise problem. So especially in the nucleon, for larger time distance, we get the noise is increasing exponentially. You can see this basically here. It's on the physical point, effective mass of the nucleon. And at some point, the noise explodes. And it's rather difficult to get the ground state. So here are different combinations. So this is a 3-state fit starting from here. This is a 2-state fit starting from here, and then the plateau averages. And you see, depending on where you start, the ground state is moving quite a lot. And the question is how to improve this. One thing, you get this golden window. You get from above, you have this excited stage contamination. So the question is, are there methods to improve this? Yeah, for example, by adding multi-hadron states to your operator base. Another way is to use improved operators. And one interesting thing is here shown in the scalar case of the Charm meson, is to use optimized profiles in distillation. So one work by the Wuppertal group showed that basically doing this from some method, you get really a nice plateau by optimizing the profiles. Another bound is basically the upper bounds. They're signaled the noise bound here, and there are various methods under discussion. One possibility clearly is to just increase the statistics. And a way to increase the statistics is it's an idea by using multi-level algorithms. And the idea is based on, again, a way of decomposing the lattice. In this case, you decompose the lattice in 2 active domains with a frozen domain between them. And then you can show that the determinant, again, splits up into a global part and into parts which are then defined on this omega-0 domain, which includes the frozen part, and an omega-2 domain, which also includes this frozen part. And then the idea, one can update these 2 active domains independently by taking into account the frozen part. And this one can be done for each n1 times, and then one does a global step and repeats this. And then the hope is, or then the assumption is that the error, if you combine then all of these different updates here, in your measurements, the idea, the hope is that the error goes down with 1 over n1 times the square root of n2 from the global updates. This can be also applied to 4-dimension, and it's also well suited for parallelism, because you can update each chain in parallel. For example, you can also what you can do is you can use an existing ensemble, pick up n0 configurations, and apply on each of these configurations in parallel these updates. Yeah. So results from this multi-level work. One result is given by the calculation or application on the on calculations of the hadronic vacuum polarization. Here in case of pions at 300 MeV, where the frozen domain is given by 8, and the active domains, each of them have the time separation is 40. And what you can see is that so N0 that did this on 25 configurations, which with 10 updates for each of this domain individually. And what you can see is that here in the middle they see that they can reduce this error by almost a factor 10. So not exactly, but you see this effect that is not going with the square root. This also works well. I mean, this is known basically in pure gauge. This is known since a while. This also works quite well for agloonic observables. So Lorenzo just showed this at the lattice. For glue balls, in this case, you just freeze only one time slice. And what is shown basically here is that he used in one of these 1,000 of these different updates, and you can show that the error goes down by 1 over n and 1 linearly. So the question is, what are there are drawbacks for this method, and one is the question: how large has to be the distance between the active domains? And I think so far investigators has done for heavier pion masses of 300 MeV, where the distance were like 0.5, 0.8 femtometer. The question is, if one goes to the physical point, how large has to be the frozen domain? And this can be up to 1.5 to 2.5 femtometers. But this would be in the region, I think, Ajahn Gupta was pointing this out, where also the signal to noise starts to be increasing in the nucleon, so it might be a good match there. Okay, so let me conclude. So let me conclude with some comments about the well-suited algorithms in the future. For example, it would be a multi-level accelerated with local updates. So one can use 4-dimensional decomposition, and one can basically then do the local updates to enhance topological transitions. This would meet the hardware requirements, so one could do multiple chain by just running them on different partitions. This is also possible for multi-tempering algorithms. So you basically can run each of the chain on different partitions, and you only have to communicate for the swapping except reject step. Due to the domain decomposition, you have this communication avoiding aspect, and you can increase the acceptance rate by localizing your updates in case of this accept reject step approaches. The challenges for having this algorithm, or in general for algorithms, is that we need for sure new software solutions. For example, for multi-level or also for SON flows. We don't have open source code basis in the moment, as far as I know. For sure, one needs flexible kernels. So if you remember, all the different machines in the moment have different architectures. So to run on all of them, you need just to have kernels which are efficiently working on each of these different architecture. So in this case, maybe Grid in GPT, the Python interface to Grid might be a good candidate for such algorithm, where also DDR-HMC is available. But maybe not the Wilson Dirac, also the Wilson kernels, how good they are behaving in this package. Another challenge which one has to understand what is happening in the physical point for this multi-level algorithms, how large has to be the active domain. And I think topological open local updates are it still has to be understood how to implement them correctly in SU3 4 dimension. However, there is a bit time, I think. So the European exascale will come, I think, in 2 or a bit more years. I think Jupiter, which will be installed at Jülich, and as far as I understood is the name from the French Netherlands machine is Jules Verne, are currently in the tender phase. And so we don't know what will be the architecture, but I think we expect them that they will come. And with them, more computing resources for meeting these challenges. So.